the urgency of transitioning to clean energy is putting increasing and continuous pressure on mining companies. They need to develop new technologies for extracting these materials from primary sources and explore potential secondary sources. Modern technologies in the mining industry still focus on traditional methods. For example, hydrometallurgical processing typically involves leaching reactions in acidic environments using inorganic acids like sulfidic, nitric, and hydrochloric acids. However, recent innovations have shown that using organic acids can be beneficial. For example, there is a new recycling method for lithium-ion batteries that uses only organic acids, and this approach produces high-purity cobalt and lithium products. Additionally, the separation and purification steps of leach liquor often face economic and environmental challenges with solvent extraction and ion exchange resins. On the other hand, ionic liquids and deep eutectic solvents have shown both economic and environmental feasibility. So the well-known solvent extraction technique typically involves using organic extractants diluted in flammable and toxic solvents. However, new technologies are emerging that aim to replace these harmful reagents with non-toxic alternatives, even to eliminate the need for reagents altogether, like with the membrane technology. Membrane technologies are quite exciting. They include in developing materials that separate metals and organic compounds through nanofiltration, ultrafiltration, and electrodialysis. These methods are also being explored for CO2 separation, purification, and capture from industrial processes, including recycling. On another note, the topic of deep seabed mining is gaining a lot of attention and active discussion these days. So what it is, deep seabed mining is an emerging industry looking to extract valuable minerals from the ocean floor. The aim is to obtain minerals like manganese, copper, cobalt, zinc, and rare earth metals. These minerals are found in three main habitats on the seafloor: the abyssal plains, seamounts, and hydrothermal vents. So commercial deep seabed mining hasn't started yet, but several companies are working to make it a reality. The proposed method for nodule mining involves deploying a large mining vehicle resembling a three-story tall tractor to the seafloor, and once it's there, it vacuums the top 4 inches of the seabed, sending sediment, rocks, crushed animals, and nodule up to a vessel on the surface. And on the ship, the minerals are sorted, and the remaining wastewater slurry consists of sediment, water, and processing agent are discharged back into the ocean. The ocean holds a vast wealth of mineral resources, some in unique concentrations, and legal constraints in 70s and 80s slowed the development of DC mining, but many of these issues have been addressed by the International Seabed Authority, leading to growing interest in the seabed mining technology. A Norwegian study, though, has identified significant quantities of metals and minerals from copper and rare earths on the seabed of the country's extended continental shelf. It's estimated that about 24 million tons of magnesium and 3.1 million tons of cobalt are contained in manganese crusts, which have grown on bedrock over millions of years. So this crust also hold 1.7 million tons of cerium and rare earth metal used in alloys, along with other rare earth metals like neodymium, yttrium, and dysprosium. However, Norway's deep-sea mining plans have faced heavy international criticism. Currently, 24 countries, including 7 EU nations like Finland, France, Germany, Portugal, Spain, and Sweden, are calling for moratorium or pause on the industry. And multinational companies such as Google, Samsung, Northvolt, Volvo, and BMW have pledged not to source any minerals from the seabed. So improvements in existing technologies could reduce the need for primary critical minerals. For example, geologic AI builds high-end core scanning solutions with sensors, digital core table, and modeling capabilities. Their AI-powered tools provide geologists with accurate and high-quality data, making the analysis process more efficient and accessible. IROX technology is another innovation delivering short and high-intensity bursts of energy with pulse power technology to efficiently shatter mineral ore. Lilac technology is working on high-performance, low-cost ion exchange approach for extracting lithium from brines, known as direct lithium extraction. This method eliminates the need for traditional evaporation ponds and supports the growing lithium-ion battery market and the EV revolution. Electroflow Technologies is developing an electrochemical process that uses lithium selective electrodes to convert saltwater brines into lithium chemicals for batteries. And the process is ideal for brines with a low lithium content. It reduces the need for excessive chemicals reagents and offers high scalability with a modular cell stack design. The International Energy Agency says that to reach net zero emissions by 2050, we need to boost the supply of critical minerals by 3.5 times by 2030 to meet energy demands. And their analysis of more than 100 mineral projects, mostly involving cobalt, copper, graphite, lithium, manganese, nickel, rare earths, lanthanides, or zinc, reveals that nearly 60% of projects reported pre-production delays ranging from several months to several years between 2017 and 2023. Okay, here we are. So the three biggest reasons for delays in developing critical mineral deposits are permitting issues, technical issues, and commercial issues. Sustainability concerns, especially environmental issues and stakeholder opposition, also significantly contribute to these delays. In addition to reducing the risks of extra upfront costs and preventing early-stage project delays, there is a growing emphasis on consolidating ESG standards, and this raises questions about the accuracy of mineral resource assessments and the quality of mine design reports. And our company not only offers software for deposit modeling and mineral resource estimation for critical minerals, but also provides services for exploration design, open pit and underground mine design, preparation of exploration reports, and calculation of reserves and resources. Our reference list includes projects for developing deposits of titanium, graphite, zirconium, beryllium, and more. What we see that greenfield projects are taking off fairly quickly, but the ore deposits of critical minerals often involve complex ores that are tough to enrich and process. This requires a modern and tailored approach to assess the economic viability when providing consulting services. When providing consulting services, the companies also must offer effective tools for project coordination and optimize the selection of laboratories, technological programs, and initiative from specialized institute engineering companies and R&D centers, which is what we do. Another trend we've encountered is that the updating and reevaluation of previously mothballed deposits and or occurrences under new economic conditions. Such projects also often face unique challenges when performing pre-feasibility study, including previously completed underground or open pit mine workings, uneven sampling networks of ore bodies, lack of geometallurgical studies, and sometimes even partial or complete lack of data on wells and mining site location.